Here's an example of polynomial division. So we have a polynomial p of x, which is a cubic, and another polynomial, which is a lot smaller. It's just a monomial, right? That's just a first degree polynomial, a straight line, q of x. And I want to divide that 1 degree polynomial into the third degree polynomial. I want to see how many times I can fit q of x into p of x. And then I want to decompose the big polynomial in terms of the smaller polynomial and then plus some remainder. So this is the exact same thing that we just did with real numbers, but now we're going to do it with polynomials. Okay, so let's work on this division first. If you want to divide q of x into p of x, the long division notation was this. Right, the dividend goes inside the garage, the divisor goes on the outside of the garage. So we are going to take q of x, which is, in fact, we're going to need a lot of room. So I'm going to take x minus 5, and I'm going to put p of x inside the garage. Okay, so let's perform this. And notice the similarity between long division of polynomials and long division of real numbers. We're going to look at that leading term right there in q of x, and we're going to ask ourselves, how many times can it fit into the leading term there, 2x cubed? So effectively, I'm asking x times what gives me a 2x cubed? Well, I need a 2, and I need 2 more x's. And now we run that backwards. Multiply 2x squared by x minus 5. You get 2x cubed when it hits the x, of course, by design. And then when it hits the minus 5, you end up with a minus 10x squared. All right, wrap that in parentheses because we are going to subtract, just like we did with real numbers. So when I take 2x cubed and I subtract 2x cubed, I get 0x cubes. And then how many x squareds do I have? I start out with minus 4 of them, and then I subtract minus 10 of them. So this is why it's so important to have these parentheses there. You want to subtract off the entire result. So when you go through this, minus 4 plus 10 gives you a plus 6x squared. And you can think of this as bringing down everything else, just like you did with the real numbers. Or you could I like to think of it as, I've got a minus x here, and I'm subtracting no x's down here. So I still have minus x. But either way, that minus x comes down, and 2 minus 0 gives you a 2. All right, now that we're here, we repeat the process. So I ask myself, x goes into 6x squared how many times? I need a 6 and an extra x. And again, we do this backwards. So 6x times x minus 5 is going to give you a 6x squared minus a 30x. Wrap that in parentheses because you want to subtract the entire thing. Now 6x squared minus 6x squared gives you 0x squareds. How many x's do you have? Minus x, but then plus 30 of them. So 29 x's. And then how many constants do you have? You've got plus 2 minus nothing. So you still have plus 2. All right, let's keep going, because I think we can do this maybe once more. How do I go from x to 29x? I need a 29. Now running this backwards, 29 times x minus 5 gives us 29x And then 29 times a minus 5 gives us a minus 145. Wrap that in parentheses because we are going to subtract it. And let's see here. So I don't have any x's now. And the constant that I have is 2 plus 145. So 147. So notice once I hit that 147, I can't go any further because there's no x's there. There's no way I can go from x to something that doesn't have any x's in it. So I'm done. I can't go any further. That 147 has to be my remainder. So let's work on this part of the question now. Decomposing the big polynomial, the p of x, into q of x times a quotient in x plus that remainder. So p of x, I want to write as q of x times n of x plus a remainder. So q of x was the x minus 5. And how many times were we able to fit x minus 5 into p of x? That's exactly what's on top of the garage, right? That's the quotient. So we multiply by 2x squared plus 6x plus 29. So we've got q of x times n of x. And now we need to add our remainder. And our remainder was a constant 147. Now, don't trust me here. In fact, let's actually go through this and show that this actually is a good decomposition of p of x. So when we go through this algebra, we should end up with p of x back. If I distribute that x through this parentheses, I get 2x cubed plus 6x squared plus 29. And then when we distribute the minus 5, we end up with minus 10x squared minus 30x minus 145. And then we still have that plus 147. And by combining like terms, we end up with a 2x cubed, a minus 4x squared, a minus 30x, and a plus 2. Oh, did I do something wrong? We didn't get what we wanted to. Let's go through this real quick. Let's see. If I send this x through here, I get a 2x cubed plus a 6x squared. Oh, that's a 29x. And then let me double check the rest of the terms. The minus 5 gives us a minus 10x squared, a minus 30x. Okay, that one's okay. Okay, yeah, I was just missing an x right there. So when we simplify 2x cubed right there, I've got 6 and minus 10, so minus 4x squared. I've got plus 29x's, minus 30 of them, so minus an x, and then plus a 2 from my constants. Now this should be p of x. That should be 2x cubed. 2x cubed minus 4x squared minus x plus 2. Yep, that's exactly right.